Oops, sorry. Something like this. Thank you very much for inviting me as a visiting professor to your 3-in-1 program. It's a great pleasure and honor. I'm very well aware that University Brawijaya, it's a very big university, as young as me, as a matter of fact. You have 18 faculties and almost 30, over 20,000 students. So that's very impressive. And even I'm equally impressive how many participants I have today. Something like 100 or even more. That's fantastic. Thank you very much for Dr. Hanadia Almira for all arrangement and being in touch with me. We are also going to have another session on this Friday. But now, dear colleagues, dear professors, dear teachers, dear students, I take you to a journey on adhesion in dentistry and advanced resin-based composites. My presentation, it's not going to be too theoretic, so don't worry, I'm not going to annoy you too much with the deep-going physics or chemistry, but just important main features will be included. Also, aspects on what is good in dental resin composites and what is not good today, what needs further development. So I hope this would be clinically pleasant to follow and would give you even more consolidation in your present day knowledge of dental resin composites. So for the first, very briefly, I have made a long tour in my academic career, which is surprisingly short, because I was something like 40 years old when I realized that I still would like to do something different in my life. And then I was knocking the right door in Turku, Finland, and I got accepted as a PhD student. Thereafter, I had a few visits to Groningen in the Netherlands, the dental school, also at the Nordic Institute of Dental Materials in Oslo, Norway. Then I spent 12 fantastic years in Hong Kong in China, and during those years I was frequenting many Indonesian universities. Universitas Sultan Agung in Semarang, Universitas Muhammadiyah in Yogyakarta, Universitas Gadjah Mada in Yogyakarta, Universitas Indonesia in Jakarta, at least. I met plenty of wonderful colleagues. I can't forget the hospitality in your country and the tasty Indonesian food, let alone nasi goreng is one of my favorites still today. But also I could see the high quality of dental research and teaching in your country. Now, currently I'm a professor of applied dental sciences at the University of Manchester. I like my current title because it means that I can research and teach actually whatever I want in the field of dentistry. So if you once in your lifetime happen to be in Manchester, so please give me a call and we could have a cup of coffee together. I can't promise I could find my favorite coffee, Kopi Luwak, but something else, definitely. During my presentations, I encourage you to make notes on a piece of paper, piece of jotter, and creating for yourself a mind map what we are talking about. Maybe that would give some questions for you to also consider. So, so the contents of today contents of today include dental adhesion, something about wetting, something about surface properties, dentin primers, principles of dentin bonding, and then something about resin composites and resin composite cements. And then we got quite a few challenges because we don't have an ideal restorative material yet. I'm also touching a little bit 3D printing and the recent advances in resin composites. So be very much welcome. You are all very much familiar with resin composites. You know how to etch the tooth tissue. You have a very good idea about dentin bonding agents. When we have the chance to have questions and answers, so please don't ask me what's my favorite resin composite or what is my favorite bonding end agent or etchant. I try to avoid the commercial brands. I want to be a neutral researcher and teacher in this respect. If you want, I'm happy to provide the handouts of this presentation afterwards. I'm following quite tightly the presentation I have in front of me. So it all starts with the oral environment, with the oral microbiota pellicles that are forming biofilms. Biofilms are everywhere in human life, as we all well know. They may expose challenges in dentistry, as we very much are aware. Oral microbial communities, they contribute to human health by fine-tuning immune responses and reducing dietary derived nitrate. And in any environment, the concentration of any particular molecule is very likely to be higher or in the proximity to a surface. We are going to talk very much about surfaces. Surfaces in the oral environment, surfaces of the restorations. And different species of microbes often act together to exploit a habitat. These consortia are usually presented as a biofilm growing on the surface. The surface provides the physical support and allows the community to stay together. The mouth comprises a number of quite distinct habitats, most of which are bathed in saliva. So we have saliva everywhere, we have oral microbiota. This is how it starts. So on the left-hand side, we can think that we see a surface, an enamel surface. What happens is saliva flow creates a shear force and is dislodging some of the attached bacteria. More exposed bacteria experience a greater shear force and they are easily removed. However, when we have pits and carious lesions, the bacteria are protected from shear force and will easily remain. And before plaque can accumulate, the tooth has to be colonized by bacteria. And as you well know, these challenging first colonizers are streptococci, namely Oralis, Mitis, and Sanguis. The surfaces of all cells, they are negatively charged because of the presence of proteins and other cell membrane components which contain phosphate, carboxyl, and other acidic groups. And nearly all non-biological surfaces are negatively charged. These are things we may not necessarily always think about. Let's take a look at this picture. This cartoon is it's created by my colleague Dr. Akikazu Shinya at Nippon Dental University. We can see here a one-unit bridge. If you see the insert on the right-hand corner, we can imagine how pellicles, and biofilms are formed on the surfaces of the teeth and also on the surfaces of the restoration. So restoration surfaces are not free of the same challenges what we have. But what happens during biting? If you place such a 1-unit bridge on your patient's between two tooth abutments that you have prepared, the restoration is experiencing biting forces, which you see as the blue arrows on the cartoon. Bending moment, so the restoration is definitely bending. Even a fraction of millimeter matters. Bending is comprising tension on the opposite side of the restoration. There is compression to the tooth abutments. What is applying the restoration itself is twist and torsion. So we have all the time the biological challenges in the oral environment. We have the physical stresses and strains created by biting forces. And then we have adhesion, because this restoration must have been cemented in a way or another. So as we can easily see, this is like engineering sciences. Adhesion. What is adhesion? We talk about adhesion very much. So let's take a little journey. So adhesion is a concept. It's telling about a tendency of two materials to hold together. A given surface is said to be hydrophilic when a strong affinity for water is readily wetting over the surface without the formation droplets is happening. So some surfaces are hydrophilic. The term is in Greek and means like loving water, very simply. Then we have a hydrophobic surface. It means that the cohesive forces with the bulk water, they are greater than the forces in the interaction of water with the surface. And in normal life, we have plenty of examples. Silicone surfaces, polytetrafluoroethylene surface, waxes, oils and grease in general. Then we have a concept. We are very seldom measuring it, but we need to understand that we have the so-called surface free energy that is everywhere when we are talking about adhesion. What is surface free energy? It's about the forces between the surface and the water are much bigger than the cohesive forces within the bulk of water. Let's proceed to see a closer look. Material surfaces with a special affinity to water, they are known hydrophilic, meaning that water is spreading across, maximizing the contact with the surface. And those that naturally repel water, they are hydrophobic. Adhesion is the bonding of dissimilar materials by attractions of atoms of molecules. So we have different materials bonded together. As we well know, in dentin bonding, hydrolytic degradation is reducing adhesion. This happens all the time, regardless whatever you clinically might try to do. Resin composite fillings, they have their lifespan. If very lucky, a resin composite filling may last 7, 8, even 10 years. But the problems will start growing gradually. The brown stains around the adhesive borders of the filling, for example, cemented crowns may fall out. Now, there are two mechanisms of adhesion which we can present: chemical and mechanical. The mechanical part is basically quite easy. We are talking about retention, micro level or nano level. And retention quite simply means that things are interlocking in a way or another. And dentin bonding is mostly understood to be based on mechanical retention. However, as we are going to see, some aspects are related to the chemistries. Chemical adhesion is actually bonding at the atomic or molecular level. Mechanical adhesion is the retention by the interlocking or penetration of one phase into the surface of the other. These are micromechanical and nanomechanical interlocking mechanisms and approaches. So micromechanical just means that the parts trying to make the retention, they are very small, and in nanomechanical, they are even smaller. However, we can't separate these things. Chemical and mechanical adhesion, they take place together. And the modalities of adhesion, we can list four. Chemical bond may take place between the adhesive and the substrate, the material we want to adhere. Electrostatic forces as static electricity hold the substances together. If we have something negatively charged or positively charged, so they are attracted by each other. Then we got van der Waals forces, which may develop between molecules. So if you think about petrol you are using in your car, a bottle of petrol, it's easily evaporating. And those molecules, they are held together by van der Waals forces. They stick together, but not very strongly. Then I should like to mention as one of the modalities of adhesion, moisture-aided diffusion. Namely, when this takes place with a glue into the substrate, it will be followed by hardening. And a very good example is, for example, cyanoacrylate glues, also used for treating smaller cuts on the skin. So we can glue the skin back together. So adhesion, it's a very complex thing indeed. And these are the modalities how adhesion may take place. Retention with resin composites has been achieved by etching tooth enamel with phosphoric acid or in acrylic acids, which is the case if you are using glass ionomer senates. And please let me remind that we may have differences in some clinical procedures depending on the country and region. So not the clinical guidelines are similar in each and every country. We may do something in a different way here in the UK. Adsorption of gases or liquids is common onto the surfaces of liquids and solids. In adsorption, a liquid or gas adheres firmly on the attachment of molecules to the surface of the solid or liquid, and thereby the surface free energy will be reduced. And this wouldn't help with the adhesion, because for successful adhesion, we need high surface free energy surfaces. If the surface free energy is low, adhesion won't be durable. Natural tooth surface, glass, porcelain, they are readily wetted by water, which is forming a very thin layer of water molecules. And if we think about the wet human enamel, we all know that the natural, pleasing, aesthetical look of our teeth is based on that the teeth surfaces, they are wet all the time, right? And very interestingly, if we think about the wet human enamel surface, if we try to dry it, if we try to desiccate it, so the first water to evaporate is bulk water, and physically and chemically adsorbed water would remain. And this is something we can only do in the laboratory experiments, apparently. When more heat is applied, physically adsorbed water leaves, and if more and more heat is applied, and now we are talking about hundreds of Celsius grades, then the last chemically bound water leaves. Adsorption and absorption, they differ as processes you may have come across. So, but the message of this slide is that we are always working with wet surfaces in dentistry. Whatever we try to do, whatever we want to do, the surfaces, they are never dry. We have to cope with wet bonding. I mentioned adsorption and absorption. So in absorption, the substance absorbed diffuses into the solid material by a diffusion process. And this process is not noted for concentration of molecules at the surface. If we have both adsorption and absorption, and if we are not really clear which process is predominating, then the general term for this is called sorption. We are talking about the sorption properties. Resin composite filling materials, they can absorb some amounts of water, as we well know. Now, on this slide, we see a few key molecules we will be familiarizing each other. And I promise to you that not too much chemistry, so you shouldn't feel uncomfortable. MDP is a very important molecule in dentin bonding. Very interestingly, on the left-hand side, we have a methacrylate group that's ready to polymerize. Then we have a long zigzag part, which is a linker. And then on the right-hand side, we see a phosphate group. Then in the middle, we see the bis-GMA molecule. I know it looks terribly complex. You may wish to pay attention that we have got benzene rings. We have got hydroxyl rings here, symmetrically almost as a mirror image. And then we got methacrylate groups for polymerization. Triethylene glycol dimethacrylate is used in resin composites to adjust the resin matrix. So in dentistry, adhesion of any primer, restorative cement, luting cement, or pulp capping agent takes place on a wet surface. And we never have a really dry hydroxyapatite surface. Dry hydroxyapatite surface apparently would be very simple, but nothing is simple in dentistry. We are dealing with a very complex health science field. However, it's most rewarding and exciting from the point of view of dental research, for example. I mentioned already something about high energy surfaces. So let's now make the definition clear to all of us. High energy surfaces, they are found on clean metal surfaces, which are readily for absorbing molecules. Low energy surfaces, they happen to be those surfaces that are very much hydrophobic. Silicones, oily, greasy surfaces, waxes, polytetrafluoroethylene. If we try to glue something on these surfaces, the success rate would be very much low. So high energy surfaces, low energy surfaces. This is a simplistic cartoon, but I somehow like it because it's so clearly describing what may happen if we are not careful with the cementation. So if we have like a ceramic crown, the adherent in this case, if things go unluckily after etching and silanizing the ceramic surface, there may be air pockets uh, compromising that we would have the whole adhesive surface included. Now, a couple of terms you may write down on your notes and then read afterwards. An adhesive is a material forming a layer between two bodies that, through wetting, specific bonding, or mechanical key, holds those bodies together. The adhesive must provide good wetting on the adherent, and the adherent is a body treated with an adhesive. So an indirect restoration is an adherent. An adhesive is your luting cement. The adhesive should have suitable viscosity for easy clinical work. The setting of the adhesive should take place without excessive dimensional changes, so we don't want the things to expand or contract, at least not too much. Then, very surprisingly, the thickness of the adhesive layer, it's a very important question. And it would be wrong to think that, hey, now I'll apply a very thick layer of adhesive to achieve a durable, good adhesion. And this is not the way how it goes. As we all know, the film thickness of cementing, for example, a dental crown, it's quite thin, but it's enough. So the strength of the set adhesive must be taken into consideration. Cohesive failure of a bond takes place if the adhesive fails. The adhesive may fail if the layer is too thick. An adhesive failure takes place where the adhesive and the adherent are meeting each other. If the surface we are planning to cement, if it's not clean, if it's not cleansed as clinically instructed, the adhesion has little chances for success. Now, let's take a tiny wee break with this slide and have a look. We have been talking about quite complex concepts. On the right-hand side, we can see we have the green, the dark blue, and light blue substance here. And adhesion takes place at the interface, as shown on the right-hand side. And cohesion takes place, for example, within the adhesive layer. And on the left-hand side, we can see how an adhesive cemented system may look like. One of the features in dentistry what comes to adhesion is that we are always talking about very small surfaces. And when the surfaces are small, then the question is that the adhesion must be durable. Maybe a few words about surface-free energy. As I said, we are never measuring this, but it's a concept we should be aware. So the ability of an adhesive to wet the surface of an adherent can be measured by the contact angle using a sessile system. So we drop a tiny wee droplet and see what happens. Does it spread on the surface or does it form a drop? Materials of low surface energy will not be wetted easily or at all. Waxes, silicones, greases, and polytetrafluoroethylene. Surface-free energies can be increased by appropriate surface pre-treatments. So the surfaces must be handled in an appropriate way. Acid etching of dental enamel or acid etching of ceramic, they are surface pre-treatments. Excuse me. Also, grit blasting of, say, a metallic surface or zirconia surface, they are also surface pre-treatments. Priming with a dentin bonding agent is also a surface pre-treatment. Now, please, if you take a quick glance, I was mentioning the contact angle, and just to make sure everyone is feeling comfortable, we may take a look. I mentioned an experiment, if you take on the upper part of the slide, where we drop a very, very small drop of water, for example, on a surface, and if it doesn't spread, we can see that the contact angle is very big. So the drop remains. In the middle, we see something where the surface tension is still relatively high, and the contact angle is 90%. But in the lower picture, the surface free energy is very high, and the surface tension is very small, and the drop is spreading on the surface. And measuring contact angle is very good in research of adhesion. It's a balance of surface-free energy and some interfacial energies if you want to go to the scientific explanation. The increased wettability of solids with liquids of reduced surface tension is important in many dental applications. The wetting power of a liquid is its tendency to spread on the surface of the solid. If we are using wax patterns, they should be wetted by water or water suspension or plaster when you are proceeding to the casting investment. However, these parts of wax must be treated with a dilute solution of some wetting agent. Detergent, like a dishwashing liquid, is very good in this respect. We are nowadays more and more 3D printing everything. Many metallic restorations are already attempted, at least at the laboratory level, but counting on cast methods in dentistry are still everyday things. For molten metals, wetting of surface by liquids is enabling spreading of a molten flux on hot metal during melting or soldering operations. Some antifluxes, such as graphite, can be used to paint portions of metal surfaces where solder is not wanted. I'm just very briefly mentioning these things. Surface tension of metals is relatively high in comparison to other liquids. This is why greater cohesive forces exist between the liquid air surface, than between molecules of liquid compounds when we are thinking about ethanol or water. Surface tension of molten metals is reduced with an increase in temperature. The metal should not be oxidized excessively or otherwise damaged by heating to the elevated temperature. So this is why we have to pay attention of the melting temperatures and procedures. Suitable flux will help prevent damage during heating. So I think we don't dwell too much in metallurgy. Dental silver amalgams, they are still used in many parts of the world. In some countries, they are discouraged. In the UK, if you really want, you still may get an amalgam filling, but it's getting more and more difficult. In mixing amalgam, it's very important to increase the degree of wetting the amalgam alloy powder by mercury, which is the liquid component. In amalgam powder, if we got tin oxide or silver oxide, they can be harmful because they resist blending and the wetting reactions, unfortunately. Then a few words more about wetting. So what is wetting? Wetting is defined in terms of the degree of spreading of a liquid drop on a solid surface. The contact angle formed by the liquid surface and the interface separating the liquid and solid is used as a measure of the degree of wetting. And when we think about dental laboratories where soldering and welding may be taking place when preparing clasps to a denture or some other framework thing, good wetting is very important to the surfaces to be soldered. Hydrophobic substances, they are those that exhibit high contact angles with water. The adhesion of resin or primers to etch enamel is a result of capillary penetration into surface irregularities, and tag formation is the way we understand resin composites or resin composite cements. They are forming bond strength with the restoration. Just a few examples of the contact angles and surface free energies of various substances. I'm not saying that you should remember this the rest of your life, but just you might get an idea that surface free energy for selected substances, they can vary quite a lot. And contact angles of liquids on solids, they also may be very much different. And on these tables, values over 90° indicate poor wetting. So wetting doesn't take place, but the liquid remains as droplets. Good wetting promotes capillary penetration and adhesion and indicates strong attraction between the liquid and solid surface molecules. This is not maybe in the core scope of this lecture, but if you come across terms like sol, aerosol, emulsion, foam, you may see that they are colloids and they are based on a dispersed phase and continuous phase when these phases are mixed with each other. So foam is made of gas and liquid. Aerosol is liquid in gas. Smoke as an aerosol is some solids in a carrier gas liquid. And what is very important is dentistry is strong, durable adhesion. We are talking about bond strength We are talking about adhesive strength, which are definitely the same thing. Why is this so interesting? Let's take a look. Adhesive strength refers to the ability of an adhesive to stick to a surface and then bond two surfaces together. It may be measured by assessing the maximum tensile stress needed to unstick or detach the adhesive perpendicular to the substrate. The adhesive strength is defined as the maximum tensile stress possible at the interface, and it also means the load-bearing capacity. Adhesion may occur either by mechanical means, in which the adhesive works its way into small pores of the substrate, or by one of several chemical mechanisms. Very interestingly, porcelain fused to metal restorations, which may be also familiar to you, ceramics to metal bonding takes place in shear. The ceramic is just burnt onto the metal framework surfaces, and when they cool down, the ceramics becomes like compressed on its place. The adhesion strength results obtained in laboratory tests, they often overestimate the bond strength obtained in clinical use. And when we are reading such publications, they are very important, but we should view with some caution. Adhesion is affected by the coating thickness and the solvent retention when solvent-containing coatings are used. When an adhesive is bonded to a surface, numerous mechanical, physical, and chemical forces come into play, which may affect each other, as we already have seen in this introduction. Adhesive strength is the measurement of adhesion, or the attachment between adhesive and substrate. A variety of tests have been developed to measure the so-called bond strength between two or even more materials. And then we can think about ceramics to metals, laboratory resin composites to metal frameworks, cements to metals, and of course any polymers, ceramics, resin composites, adhesives to enamel and dentin, and many, many more. Most of the tests are designed to take place the bond in tension. I will explain what that means in a second. To simulate oral conditions, specimens with adhesive junctions, they may be subjected to varying temperature by using thermocycling, artificial aging between +5 and +55, with a certain dwelling time in each of the temperature over a certain total time equaling to thousands of cycles, after which we measure the adhesion strength. This is a laboratory process. It doesn't simulate optimally the clinical situations because of the differences in geometry of the test specimens and clinical application. Adhesion strength tests, they rarely isolate stresses to poor tension or shear. Durability is the time period for effective bonding in clinical use. An adhesive means a thin material film added to produce adhesion. Adherent is a name for the substrate to which the material adheres, dentin or enamel. Let's take a quick look at this cartoon. I mentioned something already about torsion and bending and shear, and so there are different type of stresses which cause deformation in any dental material we are using and restoration. If we have an axial force, the deformation may be then elongation or shrinking. If we have a shear force, then we apply shear forces, something like this. We may have a twisting moment causing torsion like this. So then we are like rotating on opposite directions. We may have a bending moment when we are bending the restoration. These things happen in the oral environment. I mentioned we have the adhesive aspect, we have the biological environment, and we also have these physics affecting every single restoration. However, adhesion strength tests performed in tension, they cannot be compared to those done in shear. And if you decide to measure adhesion strength, there are few available ways to carry out microtensile bond strength, micro shear bond strength, shear bond strength, and enclosed mold shear bond strength. Some testing variables, such as the specimen bonding area, may be very much different. This device is showing how we artificially can age specimens. So we have two water baths, cold and hot, and the specimens are in a basket, and then they are transferred back and forth, as long as possible. This is a thermocycling unit. Now, on the left-hand side, when we are testing adhesion, there are three modes for failure. On the left-hand side, so-called tensile opening. So the adhesive joint is opening. Number two, in plane shear. So the restoration is kind of sliding when dislodging. Then we got out of plane shear, tearing. And on the right-hand side, we are demonstrating a shear bond strength test. So we have cemented something onto something, we have a specimen, and we applied force to see how long and how strongly the restoration is lasting. How strong is the bond strength? Then on the other hand, we should take into consideration also something else. So if you are measuring like a resin composite cylinder, you have adhered on the ceramic base, and then you applied load and see how strong is the adhesion joint. And if the ceramic base has like a tiny v initial pore or tiny v crack, so what may happen is that the fracture is taking place in the ceramic base, and we don't get the adhesion between the composite and ceramics. So this is just explaining that we have to very carefully plan and execute the experiments. One way could be using microtensile bond strength testing. We may have resin composite blocks adhered to a ceramic block, and using a blade saw we are cutting until we get small specimens like this. This is what we call microtensile bond strength. Another illustration and how we are getting the results. Here is a failed specimen, and we have recorded some reading for the adhesion strength. These are very much used everywhere, requires meticulous preparation and work behind. Then adhesive layer may fail different ways. Here we can see A and B. Cohesive failure is taking place on the cement film. We may have interfacial failure where the restoration is failing here. Then the failure may be mixed. So there are adhesive and cohesive failure taking place. And as on the previous slide, we may have a combined cohesive failure or the adhesive adherent. So the material is also failing. And then very much important is to carry out microscope or scanning electron microscope assessment for failure mode. This should be carried as a standard procedure in the laboratory. Now we are proceeding. How much do we have time?
2 hours, Prof.
Yes, we are now proceeding to dentin conditioning. Thank you very much. A so-called smear layer refers to a layer of debris on the tooth surface, which comprises residual inorganic and organic components. This layer is produced whenever the tooth structure undergoes a preparation with a burr. The smear layer will fill the orifices of the dentinal tubuli, forming smear plugs. This is how we understand. These smear plugs decrease dentin permeability by 90%, and the smear plug alone can prevent adhesive resin penetration into dentinal tubuli. The thickness of the smear layer can range from 0.5 to 2 micrometers, and for the smear plug, the length is 1 to 10 micrometers. The smear layer poses some threat for optimal bonding to take place. And this is why it needs to be removed. For example, the smear layer needs to be removed prior to bonding by etch and rinse, the total etch and adhesive. This will lead to a thicker hybrid layer and long, denser resin tags, which result in better, durable bond strength. Dentin bonding refers to a process of bonding a resinous dentin bonding agent to conditioned dentin, where the mineral component is replaced with resin monomers to form smear layer, comprising dentin collagen and cured dentin bonding agent. A so-called dentin bonding agent, we are also talking about the dentin conditioner or dentin primer, is used to remove the smear layer and to alter the dentin surface by partially demineralizing the intertubulary dentin. And what are these dentin conditioners? They include phosphoric acid, nitric acid, maleic acid, citric acid, and ethylene diamine tetraacetic acid, EDTA. These are dentin conditioners. The partially demineralized dentin acts as a hollow scaffolding which can be perfused with the dentin primer. Over-etching with phosphoric acid as well as over-drying of the dentin may lead to collapse of the collagen network, making infiltration of the dentin primer difficult. However, sclerotic dentin requires a longer time of exposure to the dentin conditioner compared to healthy dentin. This is also important to bear in mind. Some dentin conditioners contain a chemical called glutaraldehyde, which reinforces the collagen matrix and is preventing its collapse. I'm here using a few Professor van Merweg's very nice illustration. So here we see SEM micrographs illustrating enamel and dentin after treatment with polyalkanoic acid conditioner, PAA. So we are not talking about phosphoric acid this time. You can see how the enamel looks like after etching and how dentin may look like. This SEM picture is illustrating a loosely organized collagen fibril arrangement exposed in phosphoric acid etching. So when things go nicely and carefully, we have here the dentin surface and the collagen fibrils. They are nicely and neatly organized like this. Application of phosphoric acid to dentin will result in partial or total removal of the smear layer and demineralization of dentin. The etchant will demineralize the intertubular and peritubular dentin and then open the dentinal tubuli while exposing the collagen fibers, hence increasing the microporosity of intertubular dentin. Dentin will be demineralized by up to around 7.5 micrometers, depending on the type of acid used, time of application, and acid concentration. These are important parameters. The primer system, including a dentin bonding agent, is designed to increase critical surface tension of dentin, which gets decreased after etching of acid. So again, surface tension goes down and the surface free energy goes up. Moist bonding technique has been shown repeatedly to enhance bond strengths of etch and rinse adhesives because water preserves the porosity of collagen network for monomer interdiffusion. So modern dentistry, adhesive dentistry as we are calling it, is universally adhesive and tissue-saving dentistry and minimally invasive. So we are talking about conservative dentistry. We would like to preserve as much as sound dentin as we only can. The adhesive dentin interface forms a tight and permanent seal and bond between dentin and resin composite cement or filling material. Dentin bonding can be accomplished by either etch and rinse, which we also call total etch, or self-etch adhesives. Now the important point is that these methods may be applied in different countries and regions different way. And please don't ask me which one is the best way. I'm not going to tell you. Just follow what is written in the published publications. I don't want to guide your thinking too much in this case. If you have found your ideal way for dentin bonding, just follow your own instincts. In etch and rinse, acid will dissolve the minerals to a certain depth and leaves the highly porous dentinal collagen network suspended in water. Then the collagen network is infiltrated with resin monomers when things go ideally. After chemical polymerization, these monomers happen activated by light cure, it will result in a polymer collagen biocomposite structure, which we also call as the hybrid layer. Dentin bonding agents are resin-based materials which are used to make a dental resin composite filling material adhere to both dentin and enamel. They are often methacrylates with some necessary volatile carrier solvent such as acetone. Dentin bonding agents may also contain diluent monomers. For proper bonding of resin composite restorations, the dentin should be conditioned with phosphoric acid to remove the smear layer, which is created by mechanical treatment with a dental burr, and expose some of the collagen network in the organic matrix of dentin. Adhesive resin should create the so-called hybrid layer, which consists of a collagen network exposed by etching and embedded in adhesive resin. The hybrid layer is an interface between dentin and adhesive resin, and the final quality and adhesion strength of dental restoration depends greatly on its properties. The hybrid layer is, however, hydrophobic, it's acid resistant, and it's very tough. The quality of hybrid layer formed decides the strength of the resin-dentin interface. When the hybrid layer becomes thicker and more uniform, the adhesion in the bonding system strength is better. Now, current dental adhesive technology follows either an etch and rinse or self-etch approach. Functional monomers in self-etch adhesives are designed to chemically interact with hydroxyapatite of the teeth. However, the structure, size, orientation of enamel hydroxyapatite crystals appear to provide insufficient chemical bonding sites to achieve durable bonding to enamel. At dentin, phosphoric acid may today be less preferred, as the adhesives are generally not capable to envelope the exposed collagen tight enough, so to make the relatively thick hybrid layer resistant to hydrolytic and enzymatic degradation processes. As you are aware, the use of metallomatrix proteinase inhibitors to be applied separately or mixed with a primer and adhesive appeared to retard rather than prevent bond degradation. So the bonding with resin composite, it's never for good because of these reasons we have already gone through. Degradation starts taking inevitably place. However, another strategy in search for durable bonding to dentin involves chemical interaction of functional monomers with hydroxyapatite. The main challenge for dental adhesives is to provide an equally effective bond to hard tissues of different nature. And now comes the difference. Bonding to enamel has been proved to be durable. So that's not the problem. Bonding to dentin is far more intricate and can apparently only be achieved when more complicated application procedures are followed. Moreover, usually a significantly shorter clinical lifetime is achieved than in case of bonding to enamel. Today's dental adhesives are often regarded as technique sensitive, with the smallest error in the clinical application procedure being penalized by relatively rapid debonding or early marginal degradation. These are the things that will happen. As a consequence, there is demand for simpler, more user-friendly, and less technique-sensitive adhesives. And this demand remains high, urging manufacturers into developing new adhesives at a rapid pace. So when we think about adhesion and the decalcification concept, we have two options. So on the upper slide, we may see hydroxyapatite surface and where limited decalcification takes place, and which acids can be used in this option. Oxalic acid, polyacrylic acid, certain acidic functional monomers have been suggested. And as you can see, we are not using phosphoric acid. Then the other option is to use phosphoric acid or maleic acid, lactic acid, citric acid, acetic acid. So these four acids here, they are carboxylic acid. They are like organic acids, where we may get the unstable bonding from the monomer to calcium compared up where such a bonding could be stable. And then the attention goes to collagen. We are removing the calcium minerals in this bonding option, whereas in the upper bonding option, we have limited calcium removal from the surface. Then we mentioned etch and rinse, self-etch and glass ionomers. Sorry, this picture is a bit foggy when I was magnifying it. This is classification of adhesive approaches according to the adhesive approaches and the number of clinical application steps. So on the left-hand side, etch and rinse means etching, priming using adhesive resin, or etching where we got the acid to etch and one bottle consisting of the primer and the adhesive resin. Or then we can have a self-etch system where the acid is included in self-etching primer. And then we would anyway have the adhesive resin. And in the self-etch concept, we have like all the three things seen here. They are all included here now in one application instrument. Or we can have a drop including everything. Then the real option for these bonding approaches could be a polyalkanoic acid conditioner with glass ionomer cement and glass ionomer liquid. All these have their pros and cons indeed. And here we have an schematic illustration about the interfacial structure produced at Dentin by the four classes of self-etch adhesives following their pH. So if we start looking from the left with ultra-mild, pH is around 2.5, we got a resin impregnated smear layer. When it's mild, around pH 2, we got resin impregnated smear. It goes a little bit deeper. And here above this dotted line, we have the adhesive resin. When it's intermediately strong, like 1.5 pH units, we got the proper resin tag going deeper and forming interlocking. And when it's very strong, we are below pH 1, we may see how the smear layer and tags are all integrated for bonding. So the pH during the bonding procedure plays a significant role here. Now we can take a look at here transmission electron microscopy photomicrograph illustrating the mainly micromechanical bonding mechanisms of etch and rinses, consisting about 3 to 5 micrometer hybridization layer. We can here see the hybrid layer is like this grayish area. We have the adhesive resin here. We got the resin tags going nicely and deeply to the dentin. The hybrid layer indeed can be 3 to 5 micrometers, and the intertubular dentin that extends somehow into the tubuli orifice walls, as we can see here, and resin tag formation into the opened dentin tubuli. Nice resin tags we can see here. Not maybe exactly this one, but elsewhere. Thereby sealing the relatively direct connection to the underlying pulp. So this is very much how ideally dentin bonding should go. One more representative picture illustrating the hydroxyapatite-free hybrid layer resulting from the relatively aggressive phosphoric acid etching. We see the hybrid layer, resin tag, and dentin layer is seen here, part of the whole system. So modern dentin bonding systems come as the three-step systems where the etchant, primer, and adhesive are applied sequentially. Such system can be also reduced to a two-step system where the etchant and the primer are combined for simultaneous application. And then we have the one-step system. All components should be premixed and applied in a single application. It's very much up to you which one you may prefer. So when we think about a separate primer, the separate primer is acting as the adhesion promoter, allowing use of selective enamel etching with chemical bond ability based on the use of the MDP molecule, maybe containing also photoinitiators to make sure that all areas, even in the deeper parts of the hybrid layer, will be covered by photoinitiators. And as a reminder, the MDP molecule looks like this. We got a methacrylate group and we got a phosphate group that can bond with hydroxyapatite surfaces. The methacrylate group can't do that part. Then secondly, a separate bonding agent that can be light cured immediately, and it should be solvent-free or solvent-poor adhesive resins, hydrophobic to reduce the water uptake, applied in sufficient thick layer with stress-absorbing potential, like flowable resin composites and presenting high mechanical properties, and providing a good seal of the interface. So we have to be able to seal the exposed cavity, prepared cavity. This was our part for adhesion. I know there were quite a lot of things, but I believe some of the contents were already somewhat familiar to you. Now we take a look at resin composites. So in general, we are talking about structural composite materials. They are combinations of two or more separate materials. A A composite material is regarded as any combination which has particular physical and mechanical properties. Composites, they are structural materials that are compared to the previously manufactured materials. They are generally lighter, stiffer, and stronger. Also, they are engineered to replicate and mimic naturally occurring materials. On this cartoon, we can see the several types of composites. So we may have laminar composites, a composite material consisting of two or more different layers that are bonded together. We may have fiber-reinforced composites, composites with chopped or continuous fibers. We can have, for example, glass fibers, carbon fibers, polyethylene fibers. The third is we have a particulate composite. So we have small particles. We have fillers in a composite, which are embedded. So now it's important to see that when we are everyday dentistry, we are talking about composite fillings, we are talking about composites. The initial meaning for composite is that we have blended material based on different composite. So this is the generic composite. And most materials used in present-day dentistry, they are not homogeneous solids, but they consist of two or more essentially insoluble phases. They are composite materials. There may be one continuous phase and one more dispersed phase, or there may be two or more continuous phases in them. Each of these phases contains one or more dispersed phases. Why should we be interested in composite materials in dentistry? This is so self-evident question, but I still would like to ask it, and let's find an answer. They take advantage of selected properties of each material so that the physical and mechanical properties of the composites are different from those separate phases. And the trend of today is that we are using rather composite materials than completely new classes of materials. In general, we have metal-based composite, ceramic-based composite, and polymer-based composites existing. Wood is one of the composite material. It consists of cellulose with high tensile strength and flexibility, and lignin, which binds the cellulose fibers and adds stiffness. Bone is a natural composite, and it contains soft protein collagen combined with hard, brittle hydroxyapatite mineral. So we must unfortunately now skip the bone structures and closer look. It would be most rewarding, but let's just mention very briefly. Then enamel, dentin, cementum, and muscles, they are natural composite materials. Dental silver amalgams, and we may say almost all materials in dentistry, they are composite materials for their structural classification. Dental silver amalgam consists of mercury, the amalgam powder that consists of certain metal powder particles. In dentistry, we are often talking about composite resins or resin composites. Both are fine. I'm not so sure if we should talk about composite fillings, but I know it's it's used everywhere nowadays as a term. In composite structure in general, mechanical properties such as elastic modulus, they are significantly altered in comparison with a homogeneous material consisting either of the faces alone. So there are benefits why we are interested in composite structures in general. Rapidly evolving technologies and concepts such as 3D printing, artificial intelligence, machine learning, and big data will have significant impacts in design, engineering, testing, screening, production, and quality control of resin composite materials. On this Friday, we will take a look at artificial intelligence in dentistry closer. And all these four concepts, they are already changing the landscape quicker than we can now realize. So they are here to stay. Then we are talking about composite materials in general. So factors that are affecting to the properties of all composite materials are, and we got 6 things to consider. The state of matter of the second dispersed phase, the geometry of the second phase, orientation of the second phase, composition of the continuous and dispersed phase, ratio of the phases, and then bonding of the phases. The phases have to stick together in a way or another to be durable and strong and stiff. Shall we take another look at how we are classifying composites? So they may be particle reinforced. They may be large particle dispersion strength particles. We may have fiber reinforced with continuous, aligned, continuous short fibers, and aligned and random oriented to get composites. And then something we may not be really using today in dentistry are structural composite laminates and sandwich panels. Or actually, who knows, maybe one day one of you may get interested in that. Could we find some structural composites to support successful modern dentistry? We never know. So we never should say never. In dentistry, resin composites, they are reinforced polymeric materials used for restoring enamel and dentin. We also call them filled resin, composite resins, and among friends, just composites. They exhibit a vast number of products for posterior filling material and luting purposes. And they are predominantly acrylic materials, and they are very often based on dimetacrylates. All dental resin composites, they consist of 5 major components. They all must exist, otherwise we wouldn't have a successful dental resin composite. We need to have the resin matrix, certain acrylic monomers. We need fillers. The size and amount vary. Often we have glass fillers and with some heavy elements to provide X-ray opacity. This is very important. We need a silent coupling agent because the fillers must be adhered chemically to the resin matrix. Otherwise, these composites would collapse. Then we need pigments, inorganic oxides, to get the proper shade. And to set these materials, we need initiator, accelerator, and stabilizer system. I guess this is one of the most important slides in my presentation to understand how complex materials resin composites can be. Bis-GMA, urethane dimetacrylate, triethylene dimetacrylate, these are the molecules in all resin composites today, almost all. Urethane dimetacrylate, it's a large dimetacrylate monomer, as you can see on this molecular structure, with a lower molecular weight and reduced viscosity if you compare to bis-GMA. And it's typically used in combination with bis-GMA and triethylene dimetacrylate, modulating the properties of the mixture, the resin composite, increasing degree of conversion and copolymer hardness. Just not so long time ago, we published a couple of studies where we had fluorinated urethane dimetacrylate molecule. This was with my colleagues in Hong Kong, in Guangzhou, China, and also my colleagues in Lahore, Pakistan, and Dammam in Saudi Arabia. And we found that fluorinated urethane dimetacrylate with 5% of bioactive glass fillers appeared to have similar but more stable adhesion to dentin over the time, combined with the traditional or conventional resin. In addition, water storage simulated pulpal pressure should be considered when long-term stability of resin dentin interface is investigated. However, the effectiveness and durability of an experimental resin monomer should be evaluated by using ethanol and using silanized and non-silanized filler. But the main point is that there may be reasonable, surprising alternatives to develop the adhesion of resin composites. Then we need a camphor kinone, an inhibitor to get the setting reaction run. I'm not going through this. It's just a chemically cured system. We need certain component. They are optimized for aesthetics, designed for higher stress-bearing areas. And very often, dental resin composites are classified by the particle size: fine irregular shaped particles and microfine particles. My good friend Professor Ferraken has made a wonderful publication. You may be familiar with these terms: macrofill, microfill, hybrid, midfill, minifill, nanofill. We have nanohybrid, microhybrid, small particle hybrid. So this has been one way to provide different resin composites with desired properties accordingly, paying attention to the particle size of the fillers. So very quickly, if you have a multi-purpose nanocomposite, microfill, packable, flowable laboratory composite, the filler particle sizes may vary, and the volume of inorganic filler load, you may say that we may have up to 80%, up to 62, 70. It's very high. And we always have advantages and disadvantages. Some disadvantages: higher shrinkage, higher wear, costs. These are things to consider. An important example of resin composite is posterior resin composite used in direct aesthetic restorative material. The fillers are often barium, aluminium, lithium silicate, strontium glass, boron silicate, colloidal silica, zirconia silica, etc., and pigments. They include a wide variety of restorative materials with broad range of mechanical properties, handling characteristics, and aesthetic possibilities. Resin composites, they are with adequate strength and high wear resistance and polishability and retention. However, polymerization shrinkage is something we can do very little with. There is no one ideal material available to clinicians, but the commercial materials are of high quality, and when used appropriately, they have proven to deliver excellent clinical outcomes. I think I jump over that. And this is important. When thinking of resin composites, we have advantages and we have disadvantages. Acceptable aesthetics, minimally invasive, pulpal tolerance, minimally abrasive, easy to repair and adjust, inexpensive, one appointment, may serve as an intermediate restoration before definite restoration. The disadvantages are polymerization shrinkage, high wear rate, high wear posterior area, possible bulk fracture, possible discoloration, needs optimal moisture control, need good quality enamel and dentin. The application is complex, it's technique and skill sensitive. Now, you guys may have heard about aesthetic dentistry and the so-called composite bonding. I want to mention here, it refers to a dental treatment using thin layers of tooth-colored resin composites after each other. And this is meant to improve the appearance of the teeth. Resin composite is placed over the surface of the pre-treated tooth to fill cracks, repair broken teeth, fill gaps, and improve discolored teeth. Then a few words about resin composite cements. They are used for inlays, onlays crowns, fixed partial dentures, and orthodontic appliances with slightly different clinical requirements. So the clinical failures directly attributed to the resin composite cement and resin composite fillings include loosening or loss of the restoration or prosthetic from the remaining tooth structure dental implant, wash out of the cement at the margins and then staining and recurrent caries or loosening, or cement discoloration making an aesthetic restoration clinically unacceptable. This is just something about the self-cure and dual-cure cement strengths. We can see that dual-cure cement seem to be the winners regardless which brand we are using. The first type of resin composite cement were developed to improve handling characteristics and setting properties. Metal methacrylate was the first things introduced already in 1950s. Luting cement composites are more wear resistant. They demonstrate resistance to the oral environment and offer outstanding aesthetics provided by the choice of several shades. Setting is based on cross-linking of the monomers to form polymer chains, which reaction is initiated by blue light. Luting resin composites are entirely based on dental restorative resin composites. So basically we are talking about the same material, but the viscosity is much lower. Very briefly, this was the evolution timeline of dental resin composite, polymethyl methacrylate, the first attempts, the first ultraviolet cured, visible light, some other monomers, fillers, microfill to hybrid, direct, indirect resin composites, flowables and packables, and many, many more, and the story is still ongoing. Speed light curing is something you may have heard about also in dentistry. Curing through indirect restoration, such as ceramics, is still a problem. And this is why both dual-cured adhesives and dual-cured resin composites in many ways are recommended. Heat generation with high-power photopolymerization units should not be underestimated. I mean, if we all would go to light curing using just a few seconds, we might have biological problems for gingiva and the pulp. So speed light curing is already here, but we should have proper understanding. Is it for light curing resin composite fillings or some of the indirect restorations? We are talking about like 3 minutes with a huge output of energy versus conventional, which is like 10 seconds and 1/3 of the output of the blue light. Shrinkage behavior under speed light curing conditions has been observed to be material dependent, however. This is something new we should keep on following. Indirect resin composites, they are aesthetic alternative to ceramic or posterior. They perform well and in short-term patient studies, and they can effectively supplement the use of ceramics in certain clinical conditions. They can offer aesthetic alternative for large posterior restorations. In some clinical situations, they can supplement and complement ceramic restorations, for example, one crown of dental implants. Ceramics are still very much preferred in this case. For patients with poor periodontal structures requiring occlusal coverage, stress-absorbing ERCs are indicated. Excuse me. The only shrinkage that is unavoidable is the luting cement. It will shrink anyway. I think I jump over these. This is about indirect restoration. Then we may have 3D printed indirect restorations, tooth-colored biocompatible resin, and everything seems to be 3D printed today. They can provide excellent aesthetics, marginal adaptation, high strength. However, they may be used up to 1 year according to the manufacturers and according to the indications if the permanent restoration is still coming. And then we have permanent 3D printed crowns as well of resin composite. They are not hybrid ceramics. Their longevity is not yet clinically tested and confirmed and reported, so please just keep an eye on these. And the advantages of indirect resin composite, why I'm mentioning, is that they have superior wear resistance and strength, significant reduction in polymerization shrinkage, precise marginal integrity, ideal proximal contacts and occlusal contour. They may be less abrasive than ceramics, less biofilm adhesion. They can be easily repaired and added intraorally. But they have disadvantages as well as we can see. They can be bulky, marginal fit may be not so good, and some other. I think I'm just repeating here. Blue light is used as a light curing. Oxygen inhibition is also sometimes mentioned in this context. When resin composites are cured in air, an oxygen inhibition layer is formed on the surface of the freshly cured resin composite. Water spray and ethanol could be used as momentary treatments for cleaning the surface of oxygen inhibition layer. However, it's been shown that the presence of an oxygen inhibition layer improves the interlayer shear bond strength of resin composite filling, and it should be left intact in clinical circumstances. The absence of oxygen inhibition layer would adversely affect the bond strength and lead to other troubles. Now, we are almost running out of time, but almost there are some alternatives as resin composites. They don't contain traditional monomers as bis-GMA, Tegma, or UDMA. They are claimed to contribute to lower polymerization shrinkage, less abrasion, soft operation in the clinics. Follow-up studies suggested acceptable clinical results. Epoxy resins, they are also nothing to do with acrylates. they are capable of reacting with suitable curing agents and catalytically to form higher molecular weight polymers. Here we see an example of an epoxy ring. Siloranes is one of the product to trying to combat polymerization shrinkage. The silorane resin matrix exhibits with low tendency of extrinsic discolorations. They were introduced already some 20 years ago. Siloranes are biocompatible and hydrophobic. Polymerization mechanism is reducing volumetric shrinkage when compared to methacrylate resin composites. This is how siloranes look like. So we have nothing to do with dimethacrylate. This is how they are setting: initiation, ring opening, propagation, bond forming, expansion. So you can say it's a very much different chemistry. Cytotoxicity ratings are good. They are non-mutagenic. They have high reactivity and shrink less during polymerization than resin composites. Marginal integrity are very good. Indications are direct posterior restorative materials for class 1 and 2 cavities, also cavity liner or base. Siloranes are resin composites have been described with several advantages. We can see here low water absorption, reduced exogenic staining, radio-opaque, ambient light stability, easy to handle and non-sticky, excellent bond strength. It's a very long list. Wear resistance also mentioned. However, this is still relatively novel material group and we better follow the literature. However, they were retracted from market in many countries and regions because there were problems in the silorane curing, as attractive it appeared to be. Adverse reactions with resin composites may take place. Long-term effects and systemic effects are also reported. Pulpal response is possible. Dry contact with cement, resin cement with pulpal tissue should be avoided. Incidence of allergy is likely rare. However, the incidence of allergic reactions to dental resin composites and adhesive exist in the literature, and therefore the possibility exists. So we have to be careful when handling resin composite materials. Okay, thank you very much with your patience and time with me. We have the two last slides. I have now introduced resin composite cements, resin composite filling materials, adhesion science, what is essential to dentistry, some advances in these fields, and also what are we looking for when we aim at new and better performing resin composite for dentistry. So we have some wishes and expectations. Enhancement in strength, modulus, and fracture resistance. Reduction in polymerization shrinkage and the stresses polymerization shrinkage is associated with. Also, adhesion to tooth surfaces without special surface preparation or application of bonding resins. So the question is, could we have resin composite materials you are just placing without any surface pretreatments? Also, inclusion of antibacterial agents or compounds capable for enhancing the remineralization potential. Is that possible? Responsiveness to the changing oral environment. That might be one avenue to go along. Wear resistance, easy preparation using 3D printing. That is already maybe behind the corner. Light curing time and speed, is there something we might gain? Or could it be based on some other resins? Right, with these words, I'm thanking you for your time. If there are any, we have time for a couple of quick questions and comments if you so fancy.
Thank you, Prof, for the presentation. Maybe student,
My
if
pleasure.
you have a question, please raise your hand. Any question?
We can also, yeah,
Yeah.
Dr. Hanadia, we can also take the questions on Friday if we got time. But if there are now a couple of urgent questions, I'm happy to answer indeed.
Oh, yeah. Maybe on Friday, Prof.
Okay, that's very fine. And I
Thank
hope
you.
you have enjoyed. Thank you very much. I know this was a massive presentation.
Yes, it's so many topic in one presentation.
My pleasure. It was. I very seldom have such a big audience, so I have enjoyed very much of having many listening to me.
Okay, maybe the time is up. So thank you for participating today. Thank you, Prof. Juga, for amazing presentation. We will see again in Friday. So I hope a great day, and we eagerly anticipate your participation at our forthcoming event. Good
Yes.
afternoon, everyone. Thank you, Prof.
Thank you, Dr. Hanadia,
Thank
for
you,
everything.
Prof.
Thank you so much for.
Thank you very much for everyone. And see you on Friday. Same time, same place.
Yes, sometimes.
Bye for now to everyone.
Bye.